Hello, it's David, back again with another accelerator build, all we seem to do at the moment. This one is for the Atari ST, STE in my case, and it's a follow-up to the one that you've seen me make before, this monstrosity, where I made a bit of a boo-boo with the alignment of the holes in my board, made it a bit too wide and had to fit this this ridiculous adapter contraption on the top. Anyway, you've seen that before, linked below, and that was a 16 megahertz accelerator with 8 megabytes of fast double speed SDRAM on there. So this is an attempt to get that back into the same package. So it's effectively DSTB1 revision 2. So trying to get it back into the appropriate package. So this is the new layout. We've had to go non-diagonally, straight aligned on the CPLD. We've got a little 7.5 by 5 mil oscillator on there. Couple of spots up there for the buffers. That's our RAM chip, and on the bottom side we've got our regulator in there and all of the passives. There's a lot of resistor network footprints on here. I shan't be fitting those in this build, but that's because my adapter board here, which is what I intend to use for my STE, my adapter board contains all of those pull-ups. So I won't be fitting all of those resistor networks, but the capacitors and the individual resistors on here will need to be fitted, as will the regulator there and the oscillator on that side. The oscillator now has a configuration option. This is new, so there's a three-way jumper here, JP. And you see that one, JP1. That is that now it chooses the supply, a voltage supply to the oscillator. If you find it difficult to get a 5 volt oscillator, you can use a 3 volt 3 oscillator, and depending on which way you solder bridge JP1 there, you'll either drive it with a 3.3 or 5 volt line. We've got an LED, a spot there for an LED, and we've still got 5 test points there. Programmer port at this end, and this shouldn't be too terrible. Now what I will do before I start, too terrible to build I should say, what I will do before I start is to make sure that I've actually got the size right this time. So here is here's our board, here is the CPU that I intend to use. This is a 16 megahertz capable 68030, so it's an MC 68000 P16. That's what it says on the inscription there. Oh, I can get the lights then. There we go. Right, so and the idea is there's two 68000 footprints on this board here, U1 and U2. U1, which is the leftmost of the two, will be fitted with pin headers to go into the socket on, in my case, the adapter board, but in the case of an ST, normal ST, a plain ST, or a Mega, that would be straight into the motherboard. And then U2, which is the rightmost pair of tracks, is designed to have socket fitted so that our CPU will plug in something like that. So I think without any further ado, it's time to get on with the soldering. And like most of my builds, I'm going to start with the hardest part first, which is the CPLD. So I'm going to get the CPLD on, because if it all goes totally wrong and I have to give up and I damage the board or something like this, or damage the CPLD, and it's not worth salvaging, I can go to a different board, before I've spent all the time and effort soldering up the rest of it. The last thing to go on will pretty much be the pin headers. Let's get on with it. Now, just while that's going on, I will mention that one of the biggest impediments to any of these projects at the moment is the lack of parts. The CPLD I'm using here, for example, this is an XC95144XL in the QFP100 format, and this only needs to be a 10 nanosecond device, and I simply can't find them. There are dwindling stocks of 7 nanosecond devices, but I wanted to build for the lowest common denominator. You can install a 7 where a 10 should be, but not the other way around, so I don't want to build for a 7 and then when the stock comes back, people have to buy the more expensive version. The 10 nanosecond one is normally around the £4 mark. The 7 nanosecond one is normally around the £10 mark. It's a bit of a difference, and it's worth me trying to aim for that low one. So I must just say a quick thank you to Exos over at the Exos forums and web store, who managed to find a few QFP100 CPLDs in a 10 nanosecond format on his shelf, and he's donated a few for the purposes of development here. So thank you very much again to Exos. Well, look at this. This is a brand new part shipped from Farnell. '64-bit SDRAM, T-254. Shabbily done. I don't know if it's worth me trying to fix this. I only need one for today. This might have to go back. I don't think I've ever seen things this badly bent. Coming from a reputable source. Just look how uneven they are. I suspect I can make it work, but look at that. Fortunately, the pin pitch on these ones is wide enough that it can be corrected. If that were the CPLD, forget it. It'll go back straight away. What do you think? We're looking at this end. I think it's okay. You see, there we go, pin number 1. Look how crooked that is. Just need to make sure I get enough solder on there that that's a proper contact. I think it is, but I'm going to welly a bit more on there just to be certain. I think that's probably a ground. Is it ground or ground or power? I'm pretty sure. That's got a lot of solder on it, and I don't see any. Don't see any bridges. I think we'll get away with it. We'll find out in the testing. So on this particular oscillator, this particular brand, pin 1 is marked by, I don't know if you can see that, pin 1 is marked by the semicircular pad. All the others have a rectangular profile. Pin 1 is a semicircular pad, and all the others have a rectangular profile. So pin 1, oops, corresponds to where the dot is, to where the dot is drawn on the top of the packet there in front of the 66. You see, so that's the pin 1. And here, obviously, you need to try and flow underneath the package. So downward pressure is required when soldering. So first things first, I'm going to hold it in place and try and run some solder onto the pad. Then I'm going to apply downward pressure and reflow. And that should run slightly underneath. Okay, so that is marked as 3v3. Oh, I've not got him. So the left hand side, as you look at it, is not connected. There we go. So 3v3 on your right. That means I need to bridge the right hand side. Not sure how much I want this to flow actually. Solder bridging is not normally the thing I practice. Might have to have a couple of goes at this. This is a bit of a first for me. I had to bridge JP1, the left on my left side, your right side only. So we've got a healthy amount of solder on both pads. Should try to introduce more. There we go. Wait for it to cool a second and then just introduce a dab more. And we see that we now have a bridge. So that should imply, we go back to the multimeter, that now there should be continuity between the power input on the oscillator, which would be that pin over there, I think, and the 3.3. No, maybe it's that pin up there. There we go. So that one should be ground. Yeah, and that'll be the oscillator out point there, I think. So we shouldn't have any continuity between ground and 3.3, and we shouldn't have any continuity between 3.3 and VCC. Right, so that's the top side done, bar the actual pins. So we'll be moving on to the bottom, where mostly it's passives and the regulator. So it's going to be a short break while I go and find my regulator. Okay, so I found my little packet of regulators here. These are different to the ones on the DFB1. These are slightly lighter weight. I can't remember the part number off the top of my head, but I will put it on the screen. So these have a different pin out. This it amazes me why they do this, but do it they do. So this one has a voltage in, ground, voltage out pin out, which I suppose might seem logical. That's different to the standard LM 1117 pin out, which I think goes ground, voltage out, voltage in. Well, it might be voltage in, voltage out, ground. It's just why would you do that? So that does need to be careful, and in fact it is labelled here on the board to avoid potential confusion. We've got V in, ground, V out. So let's get this on. This will be the first one, and then it will be time for the passives. As I mentioned earlier, I won't be fitting the resistor networks on this particular board, at least not all of them. I do need to double check. One of them may be required. I think RN11 might be required actually, but the general pull-ups aren't needed because I'll be using an adapter board which already has them fitted. But if your ST has the lower value resistor networks already fitted to the data and address lines, then you obviously don't need to fit them as well here. If you're fitting this to a stock ST, then yes, the resistor networks are recommended. It helps provide stability on the faster driven lines. Helps provide stability in general, to be honest. So, I'll find my loop, and away we go. Okay, all of our capacitors are now in place, and we're left with two single resistors and the resistor networks. The two single resistors, R1 is simply for the LED, so that can be something in the region of 1 kilo ohm, 680, absolutely fine. That's a matter of taste. And R2 is a pull-up on the internal AS int line, so that's going to be around 2K2, should be fine for that. We do need a resistor network. The resistor network RN11 is this one here, something in the region of 3K3 for pull-ups on the test points lines. Now, in theory, no, we don't need that. Not if we chose not to use the test points. I suspect I'm going to need the test points, and I might even use them for configuration. So I'm going to fit that one. The rest of my resistor networks are all about pull-ups, or rather providing a stronger pull-up on the address and data lines. And as I've said, my adapter board already contains these, so they are not required in my particular circumstance. You would need to make an informed decision on whether you wish to fit all of those resistor networks. And if you're not sure, then fit them with a relatively high resistance, something maybe around the 4K7 mark. But obviously you will know what your plans for this board are. Okay, so we've had a lovely old clean-up here of the board. This is what it's come out like. So yeah, you can see there that there's some definite screwiness on the RAM legs, but inspection doesn't look too bad. The CPLD again is not perfect, but it's not bad. The buffers look alright. I think we've got solid connections without bridges on everything there. This corner of the CPLD looks a little bit off, but gone in with the magnification. I think it's just an uneven bit of solder. And there's a slightly off coloured one towards the left of this side, but I think that's all right. Old C8 there haunting me. Not my best work with the soldering on that one. Right, so all that in theory left is to get the through hole parts on. Now, the problem once you put this through hole on, they are virtually impossible to get off. So at this point, the manual says it's time to bring in the programmer. You can use Raspberry Pi, but I have one of these knockoff JTAG programmers. Bring in the programmer and flash the firmware onto our lovely CPLD there. Now, this is an excellent suggestion with only two minor drawbacks. The first is that I haven't written the firmware, and the second is that I haven't written the firmware. Now, I know that's technically only one drawback, but it was such a significant one I thought it worth mentioning twice. So instead what we'll do is we will see if we can at least speak to the chip and the JTAG chain and erase it. Now, I've done this before in a previous video, which I shall link in now, so I'm not going to bother showing that, but I shall go away, fire this up with some 5-volt input, 5-volt ground on the bench supply here, limit it to approximately 150 milliamps, and if it doesn't go pop and if everything's okay, I shall connect up my programmer and see whether we can just run an erase on the chip. Okay, so the good news is that the programmer was able to read and erase it. There were no problems with powering it with the bench supply, and we got a current draw of only 0.032, so 32 milliamps, which is much lower than we see on the DFB1, but there's obviously a lot fewer components on here. So that was pleasing. So we're going to move on to doing the through-hole components. Now, as I mentioned previously, there are two socket markings on here. There's U1, U2, and they overlap. The idea is that U1 on the left, as you look at it, is the pin header that attaches to the board, and U2 on the right is the pin socket. So I've got these round pin header strips and some turned pin socket strips, and we're just going to pop these down here. Now, what I suggest to do is to start from the middle ones first, which doesn't mean doing them in the same order. So, for example, the leftmost is going to be pin headers. So the leftmost on this side is going to be headers here, And you see, when we've got that fitted, we can then, so that's going to be fitted like that. We can then come down the outside here and still solder the sockets as they protrude through in the opposite direction. If we do the sockets first, not too terrible with this board, but you've got to come here in between the components and the socket you've just soldered. So that's why I suggest doing it that way around. So we need to break these off at a suitable place and get on with it. So what my approach is to pin. I think I might do it slightly differently this time. So what I did in the previous time was to do one and then do the other one. No, I can't, because yes, I don't want to do these two simultaneously. So, but what I can do is I only solder one and then come back for the other one. What I was going to suggest was to mount it in either a socket or a little bit of breadboard, just to keep it aligned, and then just do a couple on the outside. So do I have a bit of breadboard here? Yep, there we go. So just gently in the breadboard there, just check the alignment to make sure that they are sitting square. I don't have them in the wrong holes, they look okay to me. And I'm not going to do the long one there, I'm going to do the one on this side. And what you don't want is to put too much heat through that breadboard. So we're just going to dab solder the ends and then check for straightness. So we'll check for the straightness after doing the first end. So we're going to go somewhat in the middle of the two sort of extreme positions there, and we're going to dab that in there. Just going to take that out and check for straightness. So just going to look down that, and that looks pretty reasonably straight to me. So we can then spin that around and dab the far end. And that's now held securely in place. We can now remove the unneeded components, get the breadboard out of the way so that we don't damage it, and we have a nice square on, or well, relatively square on, that's pretty square, set of headers to work with. So because I've anchored the two sides there, what I'm going to do is to start in the middle and work towards the edge. Those are crucial, those sockets, so I might just take a moment to try the 68,000 for alignment. Let's just again nibble that last couple of rows off. There we go. Keep those off cuts, they're always useful. So pin one up here. And that is what you would expect on this side. You would get a few have gone in, you need some slight inward pressure because of the that's actually sitting. I don't want to push it in because it's not all soldered down yet, but that is sitting really quite nicely, and I believe we'll be fine. Now what we've just seen there is one of the issues with soldering two rows so close to each other here, and I don't know whether you you caught that in the accelerated part there, but where are we? Because I was coming in from a bit of a an acute angle, I managed to fill this this hole here with solder. So we need to try and get that out. So I'm going to start with a little bit of solder wick. Hopefully it's not a ground plane or something, which will require a bit more force. But let's just see if we can encourage that out. There we go. Nice and clear now. So it's time for another cleanup, and we need to move on to the firmware. Well, here we are. I'm pleased to say that that went pretty well. Now I've got my terrible little screen, which I just use for debugging out here. It's composite and it doesn't even have enough lines on the screen to do PEL in low resolution. But front bench just finished running there. I think that's 144 something. I can't, I'll be honest, I can't read that. It's the quality is that abysmal on the screen. 1445. That is a terrible, terrible screen. But it worked. What happened when I first powered it up? It basically, I needed to translate the pinouts, because there's different pinouts now on the on this CPLD compared to the original one. So I just had to go through and translate the pinouts, and once I got it to build successfully, it worked in 16 megahertz mode straight away. In terms of the let me just turn that down. In terms of the alt-RAM, alt-RAM booted up and passed the tests, but it didn't work. It wouldn't load to the gem desktop, and what I realized was that my DQM lines, which is the mask, it's the data mask lines, which basically indicate it's effectively UDS, LDS, it's the data strobes. On this version it was reversed to on the old from on the older version, and just a different order in terms of the logic. Basically, half the chip was driving the lower half the chip's driving the upper half of the bus, and I had them backwards in this new design. So that was a simple logic change, and then absolutely, first time in effect, absolutely everything has worked as intended. So here we go. I'm in my decapitated ST mode. There's my keyboard sitting over there with a long extension. Obviously this won't fit in the case on my circumstances, because I've got an STE and I'm using this Alpha adapter board from Exos, and there's obviously no room for the keyboard there. I'd have to design a custom one to move it around and sort of sit it over here in front of the RAM, and then I think, to be honest, it'll fit. Now in a normal ST, again, you may need a relocator card depending on your motherboard, but that is now the full form factor of the actual card itself. The adapter obviously is nothing to do with it, so that's fairly lightweight. It's quite tall, so you would need to find probably a relocator for clearance, or to be in a tower case of some variety. But that's it. I think that's probably release quality now. That's version 1, and we can put that up on onto GitHub. All of the Gerbers, all of the KiCad files, all of the Verilog, I think can now go live. And what I hope to do is to be able to get somebody to help me out with why the blitter. So it's intentionally disabled at the moment. I'm just going to reset here. So basically, if we turn blitter on and we try and get something to blit, I'm asserting bus error at the moment. So this black box, this is intentional. So that's the limitation. We have no problems with the operating system working. We have no problems with when it tries to blit it causing errors. It's just that it's just going to produce black results at the moment because I'm effectively refusing to pass data. If we go into GenBench here and we do our CPU tests. There we go. We've got our results there of, again, sorry for the screen, but we're looking at 207% for integer division. We've got 106, 107% on the RAM. That's because we're running here from Alt RAM, which is faster, so the instructions execute faster. And again, 206% there on the fast RAM. So that's all behaving as it ought. If we were to turn the blitter on, again, this is a completely intentional, but you'll see that the errors, we get black errors again. So it doesn't crash, doesn't cause any problems, other than it refuses to blit into Alt RAM, and it should be able to blit into Alt RAM technically. And I kind of half had it working in the past, but turned it off because I didn't think it was reliable enough. So hopefully that's something that can be improved in subsequent versions of the firmware. And if we have a quick look at the memory speed figures again, so SDRAM, just a reminder, SDRAM is normally 3.7 megabytes per second, and that one is fixed. And there we go, we've got a read figure there for the Alt RAM of 7.7 megabytes per second. So it is over twice as fast, and the write is the same. So it's a really very substantial boost. Okay, so there we go. The second open source accelerator that we've built on this channel. Keep your eyes open. This one will appear on my GitHub repository over the course of the next week or so, with the appropriate KiCad files, Gerbers, JEDEC files, and Verilog to be able to build your own, assuming you can get hold of those CPLDs. See you in the next video.